Okay. So when we are talking about the flip-flops, the one thing that I would like to summarize is all the characteristic equations, the next state tables, and the excitation tables all in one place. So uh, if you can think of any sequential element, one is the SR latch. The characteristic equation of this is the Q plus, which is the next state, right? Q plus is the next state here. Q plus is the next state, and Q is the current state. It's the same output, but the difference is in when the state is being observed, currently or what's coming next. And next refers to the change in the clock as far as flip-flop is concerned, right? For the SR latch, the characteristic equation that we derived in the previous lecture on latches was Q plus equals S plus R complement and Q. For D flip-flop, Q plus equals D. Whatever goes into D appears at the output Q plus after the active edge of the clock. And I would, box this up mainly because what you will see in this lecture has everything to do with that characteristic equation. Q plus equals D. Then JK flip-flop, which has the functionality of SR and toggle, right? SR JK is a combination of set reset and toggle. The characteristic equation of that is JQ complement or K complement Q, which we have derived in the morning. Then for the toggle flip-flop, we have Q plus equals T and Q complement or T complement and Q, which we also derived in the morning. Well, we didn't derive it as much as we just wrote it in this format, right? So when we derived the excitation table of T flip-flop, we got T to be related to Q and Q plus this way. Hold on. There it is. That's where, oh, we derived it, yes. We derived the characteristic equation of T here. So, sorry, we had already done that. Let me come back to this page right here. So Q plus equals JQ complement or K complement Q, derived earlier. Q plus for T flip-flop, the characteristic equation is T and Q complement or T complement and Q. So these four characteristic equations are going to be available to you during exam 2 as a reference sheet, along with the Boolean algebra properties page, carrying over from the previous exam. Next, you have all these next state tables. And the goal is not to memorize this. Again, this will also be part of the clip sheet. So this will be provided to you as a resource during the exam. What we have over here are the next state tables, which essentially answer the question, if you know the inputs S, R, and you know the current state Q, do you know the next state Q plus? We do this for SR, JK, D, and T, right? So given the current state and its inputs, what is the next state? That is dictated by the next state tables. Note over here for the 1-1 state, your SR latch was not allowed, so you have don't cares over there. Next, this is a summary of all the excitation tables. You have SR, JK, T, toggle, and D, data. All four excitation tables written up in a very compact manner. And the excitation tables try to answer the question. Let's write the question. What should the user provide as excitation or input to achieve a particular transition from Q to Q plus, right? So from the current state, if I want to go to a specific next state, what should I give at the input? What excitation should I give at the input? What should I excite my sequential element with? We derived it for JK in a very detailed manner. And if you did it for SR, you would get this. But I hope from the morning lecture, you have learned the skills to be able to write the excitation tables. So in this one page, you have all the excitation tables plus from earlier the characteristic equations. So, you know, the last few slides of the flip-flop lecture essentially have all the summary, right? All the resources put together in one spot, which will be available to you during the exam. So during exam 2, you guys will have access to 3 things. One is the characteristic equations, 2 is the excitation tables, and 3 is the next state tables. So these 3 resources, you don't have to worry about memorizing them, but you do need the ability to use them to solve a design problem. For example, in the morning we designed a AN flip-flop using a JK flip-flop. So for all those kind of things, you need to be able to use these tables and resources. Please don't try to memorize them. Okay. On this last slide, in a very formal way, I have explicitly written out the process that we went over. So if you want to convert any flip-flop to any flip-flop, you start off by writing the next state tables of the desired flip-flop, the desired transition, right? That was step number 1. The step number 2 was to write the excitation, using the excitation table, figure out the flip-flop inputs of the given flip-flop. Then the last one was to derive the combinational network that allows us to get those particular inputs at the given flip-flop. So we have gone through these steps. These are just detailing the steps out in words. All right. Now let's move on to the lecture that I want to focus on the rest of the time today. Registers and shift registers. So what's the sequence of things that we are doing? Latch, put together 2 latches in a master-slave configuration, you get flip-flop. Put a bunch of flip-flops together, you get registers. So we are trying to build up that hierarchy, right? Latch was the most basic, then we made flip-flops using latches, now we are making registers using flip-flops. And specifically, we are going to look at D flip-flops because they have the very nice ability to not manipulate the bit. They just take in whatever comes at the input and then they give it at the output after the active edge of the clock. And with registers, or shift registers, that's exactly what we are interested in. We are just trying to hold a bit in position. So you can think of registers as placeholders. Placeholder for bits. I need a place where I can hold certain bits. So if I have a 4-bit register, that means that I'm trying to hold 4 bits into those 4-bit register. So think of the register as a placeholder holder. Now, in terms of shift register, you may be interested in sometimes shifting the contents left to right, right to left, or in a circular shift. So you're essentially going to take certain contents of the register and then just shift them around left to right, right to left. Maybe you do that because you might be interested in designing a counter, and we'll take a look at that as well today. How do you design a ring counter, a Johnson counter using registers? We are essentially going to rely on the shifting aspect of things. All right, so storage registers store data without changing it. Keyword, without changing it. This is just a placeholder for a bit. And the best flip-flop that suits this is the D flip-flop. A D flip-flop is a 1-bit storage register. Now, how do you know that a D flip-flop is a 1-bit storage register? Where is it storing? Well, you typically, if you wanted to represent a register, you usually use this. You just say, all right, I have, come on. And first bit, second bit, third bit, and fourth bit, right? So this is a 4-bit register, for example. So you have the first bit here, second bit here, third bit here, fourth bit here, 4-bit register. So how are we designing this using a flip-flop? Well, think of 4 flip-flops. And just for the sake of discussion, I will draw, come on, 1 flip-flop there, the other flip-flop there, and 2 more coming right up, right there and there. So the output of these flip-flops is actually the register, the placeholder. So the output Q of the register is the first bit. The output of the second flip-flop, let's call it the second bit in the 4-bit register. Then the third bit. And then the fourth bit. So you have got 4, for example, D flip-flops here. Let me name them. D flip-flop, D flip-flop, D flip-flop, and another D flip-flop. And let us assume that they are all positive edge triggered D flip-flops. And this is Q, D, 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 Q, Q, D, and Q. So as you can see, if I use 4 D flip-flops, the output of each flip-flop is what dictates the contents of the register. So if I need 4-bit register, I need 4 data flip-flops. And I can have them held in that place because I can control whether I change things or not depending on what I connect to my input, clock input. So if I wanted to change, for example, the content of bit 1, what should I do? Say I wanted to make bit 1 equal to 0, like bit in the position 1. How do I do it? Well, it's a data flip-flop. So if you wanted something like this, if you wanted to make this guy, say, all right, let me start off 1, 1, 0, 1. Right? I want this to be my contents of 4-bit register. What should I do? Well, I have to do these things. Input, 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 input. I have to give those particular bits at the input. What do I have here? I have 1, 1, 0, 1. followed by a positive edge on the clock, because these are all positive edges. Positive edge triggered. Positive edge, positive edge, positive edge, positive edge. The moment there is a positive edge on all the clock inputs, maybe they are synced up, all are synced up. So for example, maybe they are all synced up to one clock source. So like this, like this, like this. They're all, perhaps, they're all synced up. Then the moment there is a change in the CLK signal, CLK, the moment there is a positive edge on CLK, the 4D flip-flops are going to take their inputs, and those inputs are going to appear at the outputs of those 4D flip-flops. Let me call these outputs in a conventional manner. What is the convention? The convention is to call the outputs Q. So I will call this Q3 and Q2 and Q1 and Q0, right? So I've got Q3 here and Q2 here and Q1 here and Q0 there. That's how I build a 4-bit register using 4D flip-flops. And now if I want to keep them as they are, well, if I don't change the inputs, they don't change. If I don't change the clock, they don't change, right? If clock is 0, outputs can't change. If clock is 1, output can't change. If clock goes from high to low, the contents don't change. There is only one way to change the contents of those registers, which is change the D inputs, and there should be a positive edge on the clock. Only then the contents can be changed. All right. So here we have looked at how do you write things, right? Essentially, we have written some bits to the register by changing the inputs of the D flip-flops and then providing it with the positive clock edge. And what is reading the register? Well, reading the register is simply monitor the outputs of the D flip-flops. That's what reading the register means, right? So that's kind of where we are going with this. A register file stores a group of words of data. So in this case, we have 4 bits making up this group. You specify which word to read or write. Right now we wrote 4 bits into a 4-bit register. So this is again viewed from a more general point of view. There is a multi-bit storage register. We are going to use D flip-flops to make this multi-bit register. Why D flip-flops? Because they don't manipulate the data. They take in the input and they provide it at the output after the clock gets activated, right? So you have D3 Q3, D2 Q2, D1 Q1, D0 Q0, just as we had before. You take the most significant input, go straight into the first D flip-flop. You take the next most significant bit, go into the second D flip-flop. Next input, third D flip-flop. Next input, fourth D flip-flop. So the last one is actually the least significant. These flip-flops have an active low reset input, which means if I make reset go to 0 like that, what is going to happen? If I make this 0, then Q3 will be 0, Q2 will be 0, Q1 will be 0, and Q0 will be 0, and you will see a 0 appear over there, right? Then suppose I want to make this say for example C. If I want to make C appear on the 7-segment display over here, what should I do? Well, C is A, B, C, 10, 11, 12. So C it is 12 in decimal, right? So 12 in decimal is what? 8 plus 4 in binary. So I need one, I need this to change to 1, this to change to 1, this can continue to be a 0, this can continue to be a 0. If that is what I want, then I need to first change D3, D2 first, right? D1 and D0 can be zeros. So D3 needs to become 1 here, D2 needs to become 1 here, D1 needs to become a 0 here, D0 also needs to be a 0 here. Then I also need my reset to be inactive, right? It needs to be at 1. After that, it only is waiting for the clock. So the moment now you have a edge on the clock, positive edge, negative edge, whichever edge triggered that flip-flop is, after you have that active edge on the clock input, Q3 will become D3, Q2 will become D2, Q1 will become D1, and Q0 will become D0. And the way we have set it up, a C will, in hexadecimal format, will appear in that 7-segment display, right? And as you can see, all the clock inputs are one wire, so they are all synced up, which means the 4 bits are getting clocked in parallel. All right, questions so far? What is a register? How do we make one simple register? How can I view a 4-bit register? So if you want to, let me ask you this question here. How many D latches are present here? How many D latches I should use here? In the diagram below, how many D latches? So I'm going to assume that each is a positive edge triggered D flip flop. So given that each one of them is a positive edge triggered D flip flop, how many D latches are present here? Anyone? But I need a flip-flop first, right? So if I have one D latch, I need to put it in the master-slave configuration to get a flip-flop. So I need 2 D latches per flip-flop, isn't it? So if you take a look at this from the morning, I need a master-slave configuration. So I need 2 D latches to make a D flip-flop. Once I make a flip-flop, then I can use 4 D flip-flops here to make the 4-bit register. So this actually requires 8 D latches, and you will need a bunch of NOT gates to go along with that as well. So the reason why I do this exercise is because it is very easy to lose context of, once you make the hierarchy go up, it's very easy to kind of start ignoring how we constructed that hierarchy, that pyramid going up, right? So it's good to kind of ground ourselves every time. Okay, check back. What is this constructed of? a D flip-flop. How many flip-flops do I need to make that D flip-flop? 2 of them in a master slave configuration, right? So in fact, you can take a look at D latch and then try to dig into the D latch, and you will see that a D latch will require what? 1, 2, 3, 4. 4 2 input NAND gates along with 1 NOT gate. So you can keep going down to that level. All right. Next, we will take a look at a common IC. This is 74X175. It's a quadruple D flip-flop with clear. So let's see what this quadruple D flip-flop with clear chip 74X135 allows us to do. We can usually start off with trying to understand its symbol. So in the symbol, what do you have? The first thing that I notice is clock. The moment I see the clock, I see that it is edge triggered. The triangle indicates that you have the clock inputs and there is edge triggering. And it is a positive edge triggered D flip-flop behavior. The clear is an active low input, right? So that's next. That's what I look at next. It's an active low input, which essentially means that if you connect this guy to ground, right there you will have all the inputs go to 0 here, all the outputs go to 1 here. So the outputs for this chip are available both in true form as well as in the complement form. And I can, clear all of them with an active low input. So if I just ground that, I can use that to make all Qs go to 0 and all Q0 complement, all the Q complements go to 1. Then I have 4 inputs. This essentially stores 4 bits in parallel, exactly the same way we had over here. 4 bits getting stored into the register. Storing the register means essentially changing Q3, Q2, Q1, Q0 to what we want. We did it for 1100 earlier, right? So what I can do is this. Let's suppose in a different color, I make this guy 1100. I'm again going on with the C in hex discussion. Can you guys tell me what are the things that I still need in order for me to change the output? Like, will this change immediately? Will this become 1100 right away? Or do other things have to happen? You need to wait for the clock and the internal stuff so the internals are essentially related to the propagation delay for each D flip-flop. So if you ignore that, you still need to wait for the clock. What edge of the clock? What edge of the clock do I need to wait for? Positive edge of the clock. Yes. So I still need to wait for the positive edge of the clock. All right. So that's good. What else? If I have a positive edge of the clock here, will it become 1100? This will it change to this, which also means this changes to this, or something else is missing? Was it cleared? Yes, yes. So right now it is getting cleared, right? So I don't want it to clear because I want the outputs to change. So in fact, I need to, maybe in a same red color, I'm going to mark that this guy, this input, needs to be pulled up using a resistor, some pull-up resistor to plus 5 volts. So I disconnect the ground and I connect that pin to plus 5 volts using some pull-up resistor, and then there is a positive edge of the clock, and then you are good. You will have these outputs appear. So the clear has to, it has to be in the not clearing state, right? Over here, the not clearing state is shown in red. Also, this particular chip, when I say clear, it could be asynchronous clear or it could be synchronous clear. This particular clear for this chip is a synchronous clear. Synchronous clear essentially means it will wait for the positive edge of the clock. So it will not change the outputs right away. The moment you connect to ground, you have to connect it to ground and then wait for the positive edge of the clock for things to get reset or cleared. Do you need to clear every time you want a new input? Absolutely not. You only need the clear input to establish a starting point, right? So when you start using an IC, when you power things up using VCC and ground, what usually happens is ICs start in a random power up state. And that random power up state could be 0101, 1100, 1111, 0001. It's random power up state. But sometimes you might not want it to be random. You might want it to be a starting state of 0000. In that case, you use the clear input. But you only do that for the first time when you're initially powering things up. But after that, you can keep changing the D input and clock things through, and then your cues will keep changing. So you don't need to clear it every time. Does that help answer your question, Alan? All right. So we talked about the positive edge of the clock, active low input, and how you can use the clear. In this case, it's a synchronous clear, which means even if you activate clear, you still need to wait for the positive edge of the clock for the outputs to get cleared to 0. But all 4 bits get cleared at the same time. Then we talked about the D inputs here, Q true outputs, complement form outputs. Now let's take a look at the inside of the 74X175. Clearly, you need four D flip-flops. Those 4 D flip-flops are shown as 1, 2, 3, and 4. And the overall design is a positive edge triggered design. However, each D flip-flop is a negative edge triggered flip-flop, D flip-flop. So if the overall design is positive edge, but individually the negative edge triggered flip-flops are being used, you will need to invert the clock signal. Now coming to the active low clear. Here you have the active low synchronous clear. That's right there. Why did we need this? Anyone? What is that? And it's a buffer, right? So why do we need it over there? But inverted twice. Okay, so it's not changing the logic. So it's still a buffer. So why do you think we need it? Why couldn't we just have taken that input directly to the 4 flip-flops? Fan in, fan out, right? So the answer is fan out. So this particular input here, clear underscore L, is coming from some place. So if it is coming from some place and the voltage level is not a strong 0 and strong 1, we can use this buffer to make it into a solid 0 or a solid 1. Well, in this case, active low, so solid 0. And then because it is connected to 4 things, it will all work out, right? So because it is connected to many D flip-flops, not just one, a buffer can be very helpful to restore those voltage levels. Yes. All right. So what else is there? You have the 4 D inputs, right? Least significant bit, most significant bit. So whatever you provide over here will appear in both true and complements form at the output, as long as things are not cleared and you still see a positive edge of the clock. There's a question in the chat box. Why would you invert the buffer twice instead of using a regular buffer chip? Oh no, it is a buffer chip. So it is just a buffer chip, but we are sketching this up like that. The reason why we are sketching it in terms of a symbol, we are sketching it like that is because you have an active low clear. So if you see the bubble, that cancels out, right? And you are still left with that bubble to make that overall an active low clear. So those two bubbles are essentially just a diagram view of a buffer. And the outputs of the flip-flops are both available in true and complement form. We talked about that. Positive edge triggered, active low clear. All right. So I think we are all solid over here. Okay. The next chip that we are going to take a look at is 74X374. Now let us try to go through in the same manner. Let us start from all the way to the left. That tells you what? That should tell you that it is a positive edge triggered design. Things are happening based on a positive edge of the clock. Next, OE stands for output enable. It is related to the tri-state buffer. And we'll talk about that. It's an active low in this case. Then you have 8 active high inputs. All these are your 8 D inputs that you want to use to change the contents of the 8-bit register, right? So this has to be an 8-bit register. Your outputs, earlier we had active low as well as active high outputs. In this case, you only have active high outputs. Sorry, we had true and complemented forms. Now you only have true form of outputs. Indicating the contents of the register. All right, so now let's take a look at each one of them. Because it's an 8-bit register, you have 8D flip-flops. Where are those flip-flops? 1, 2, 3, 4, 5, 6, 7, 8. 8 negative edge triggered D flip-flops. We are again using a NOT gate here that is going to help us make the logic level solid. It's going to restore those voltage levels, which we are connecting for 8 different inputs, clock inputs. So clock input is active high. However, because of that inverter and the use of negative edge triggered D flip-flops, we end up with a positive edge triggered design. The outputs are in true form and complement form, but over here we are using the complement forms of the outputs, and then we are using a tri-state buffer with active low input. So this guy is tri-state buffer or 3-state buffer with active low input. So let's try to do this. What is going to happen? So I want this to happen. Let us see. I'm going to say I want to change the contents of the register to be this 1 0 1 1 0 1 0 1. If I want this at the output, the question is, can I get that done with this? If I connect this to 1, let us try to see what happens if I connect OE_L output enable. If I connect that pin number 1 to a high plus 5 volts, what happens? Well, if I connect that to high, this guy will be 0 because that is 1. If that guy is 0, all the 8 tri-state buffers will be disabled, which means your Qs will be in the high impedance state. And so on. But if I want this to be 1 0 1 1 0 0 0, right? If I want those particular, let's see if I can highlight them in blue. Color blue. So I want the blue output. How can I get it done? Well, the first thing that I need to do, change the inputs to 1 0 1 1 0 1 0 1. Next thing I need to do, change output enable to 0. Make it active, right? Enable the output, which means this guy will become a 1 there, and all the 8 tri-state buffers will now be enabled. What next? There is still one more thing left, which is positive edge on the clock. So I change all the D inputs. I change output enable _L to 0, or I activate output enable. Then I also need a positive edge on the clock. After that happens, I will see these particular 8 outputs for that chip, the 8-bit register with output enable. So we can say this 8-bit register with output enable. So from here on out, wherever you see the term output enable being used, right away you should think of the tri-state buffer and the outputs being in high impedance state being possible, right? So the outputs can be of some logic, low or high, but with the output enable terminology, they could also be in the high impedance state, which is primarily used to connect multiple outputs together, right? Multiple things, you can connect them together, and that's what you would use the high impedance state for. So for example, if you had a 8-bit bus that was shared between multiple 8-bit registers, then you would have to use output enable to disconnect certain things so that only one 8-bit register can take charge of the 8-bit bus. So what I mean to say is this. So let me draw a sketch here. All right. Let me change the template to something that is good. So suppose you have one 8-bit register here, one 8-bit register here, so on, and another 8-bit register here, right? And this is all connected to, say, another 8-bit register over there. And in the middle, you have an 8-bit bus, right? So this is connected here. Everybody is connected to this. And even this guy is connected to that, the input. So what would happen? So suppose if I say this is 8-bit here, come on. Let's see, 8, 8, 8, 8, right? So let's just assume that all of these registers that have a 8-bit output are sharing one 8-bit bus. So let's suppose this is a 8-bit bus, which is also connected to the input of another 8-bit register. So I have to use an output enable over here because I only want one of these guys, right? I only want one of these guys to take charge of the 8-bit bus. So I need to use the output enable functionality in such an application. Do you guys see that? So whenever I try to connect multiple things together, I have to use this. So let's say this is 374s, and this is also a 374. 74x374, the 8-bit register with output enable. All right, so let's move on here. Some other octal registers or 8-bit registers. There is a 74x273, which is a asynchronous clear. Asynchronous clear essentially means that the moment you make clear active, all your outputs will go to 0. It does not wait for the positive edge of the clock, right? So that's an asynchronous clear. Let's see. Does not wait for positive edge of clock to clear outputs, right? Still, it's a 8-bit register. All 8 inputs, all 8 outputs. Outputs are only available in true form. It's a positive edge trigger design, right? Next, you have 74X377. It's a positive edge trigger design. Positive edge triggered. And there is a active low clock enabled signal. So essentially what that means is, apart from using a crystal oscillator for a clock, I have an enable signal that I can use to enable the clock and disable the clock. Right? So I don't want to remove the crystal oscillator back and forth between my design to disable the clock. Instead, I'm going to use another input, an active low input in this case, to enable and disable the clock. Again, 8 inputs for the D flip-flops, 8 D flip-flops here, and all the 8 outputs of the flip-flops available in true form. So let us take a look at how the inside of this 377 chip is made. Instead of taking a look at it in terms of 8 duplicates, right? So all of this is getting repeated, as you can see. Say 8 different times you have the same structure being repeated. So instead of taking a look at 8 different versions, we are just looking at just this. So 8D versus 8Q along with the clock and enable, right? So 8D here, 8Q here, along with active low enable and a clock. So only those 4 things are being shown here. But I hope you can see that there will be 8 versions of this, right? There will be 8 versions of that on top for 7D, 7Q, 6D, 6Q, and so on, up to 1D, 1Q. All right, so let's erase this. Now let's focus on what is this. Let's try to analyze this a little bit. How are we disabling the clock? Well, first of all, it's a positive edge trigger design which is being obtained by using individually negative edge trigger D flip-flops. With an addition of this inverter and clock being active high, it functions as a positive edge trigger design because that bubble cancels out with that bubble there, logically. Now, what is this guy? AND gate, right? So let's take a look at this. I'm going to essentially sketch up the, say I choose red, and I'm going to highlight this part here, and I'm going to try to analyze this a little bit. What do you think that is? In terms of what we have learned so far, what do you think that is? It is a 2:1 mux, and the output is essentially going to the input here, the D input there. And let us see what happens when there is an enable, right? So when enable underscore L, here you have enable underscore L as the active low select. When it is 0 and 1, what happens? Well, when enable is, when enable is 0, you have a 1 there, which means you have a 0 there. What happens then? If you have a 0 there, that means this guy is not going to help at all, because that is going to be whatever's and 0. So that doesn't give you anything. There'll be a 0 there. But this guy is a 1, which means this guy is good. And it is getting 8D here. So this is 8D and 1. So it's 8D. And then that 8D appears over here. And after the negative edge of the positive edge of the clock, 8Q will become 8D. So that essentially means if enable underscore L is 0, my 8Q plus will be 8D. Right? The next state of the 8th bit output of this register will be 8D when when enable underscore L is 0. That means enabled. It is enabled. Right? Output is able to change in this case. Right? Output 8Q plus, the next state, is going to equal 8D, the new input. However, in blue, let's do the other one. When enable is 1, you get a 0 there. The moment you get a 0 there, this guy is out. This is a 1 there. That means this is in. What is that getting? Well, it is getting the old, or I should say the current state, right? So this guy will be 8Q. So that means this is 8Q. So this is 8Q. What does that mean? That means new state, next state, is the same as the previous state for that 8th bit. That's what we are doing here. Clock enable means if it is disabled, I don't change the output. It is effectively like the clock never changes after that. But in reality, it does change. So we are having that additional input that allows us to gain that control over clock input. Right? And this guy, perhaps I should sketch this in black so that there is no confusion. All right, questions about this, guys? Other 8-bit registers. One is with asynchronous clear, which means I can make all the outputs go to 0 asynchronously with respect to the clock. So at any time, I don't have to wait for the positive edge of the clock here. And then the other variant is the clock enable input, in which we use a 2:1 mux. One of the inputs is the new input, 8D, and the other input is the previous state, 8Q. So if it is disabled, it will keep feeding back what it was earlier. If it is enabled, then it will feed in the new data into the register. Okay, all right. Next chip, 74373. Do I need to remember all these numbers? No, you don't. You just need to understand the functionalities. What are the functionalities? Asynchronous clear versus synchronous clear. Output enable. Why is it used? When is it used? Latch versus flip-flop. In this case, you will see that you have a latch enable input, which is C. Instead of a positive edge triggered or a negative edge triggered design, this is based on latch input, C. This means the 74373 8-bit register is sensitive to the level of the input C. So this is 8D latches in this case. Right. So output enable, again, the same functionality. Right. So to share an output 8-bit bus, for example, which is an active low input in this case. But the latch input C that you see over here in blue, come on. the latch input is essentially saying that I am sensitive to the level of C. So when C is 1, I will take all these inputs over here and I will go to the output when C is 1. So a little bit loose, flexible control over timing. So let me write this. This is again 8-bit register. Now this guy doesn't have flip-flops, it will have simply D latches. Sensitive to level of C. So Q plus equals D when C equals 1, right? So it's the level of the clock as opposed to the edge of the clock. So I should also say this, right? N, because it's 1, 2, 3, so on up to 8. So when N belongs to 0, 1, 8. No 0, just 1. 1 to 8. Questions here? All right, let's move on to shift registers. Now we so far we talked about how can you put bits into a register, right? Adjust the input, wait for the active edge of the clock, and then as long as you're not clearing the flip-flops, clearing the register, your output should change to the new inputs. But let us see if we can use this for shifting contents of the register. So for example, if the original contents of the 4-bit register is 1000, what does that mean? Original contents are 1000. That essentially means that there are 4D flip-flops, for example, whose outputs currently are 1000. Then if you shift it right, you want this to happen. You want that 1 to move to the right, right? That 0 moves in here, 0 moves in here, and then this, if it is a circular shift, that guy goes to this. Or in some cases you might want to bring in a new bit at the left input. It depends on how the construction of the shift register is. Sometimes it's a new input that you will be able to control whether it is 0 or 1, or if it is connected in a circular shift manner, then this 0 will appear at the go around circularly. Now if there is a shift again, what happens? Another right shift. This 0 moves here, this 1 moves here, this 0 moves here, and then this guy may move here, or there might be a new input, new arbitrary input. Again, that depends on the construction. Another right shift, move 1 more bit. Another right shift. And then this process keeps going, right? Like I hope you see that you are back to where you started, right? And this can be an application for this is to send a word to a modem bit by bit. So if you're trying to do some serial communication using a modem and you want to send a 4-bit word, you do it bit by bit. And you can do that by shifting things to the right. bit by bit, which means you are clocking things through, right? So now we need some way to initialize the shift register. Well, we need some way to initialize it to 1000, and then after, as you clock things through, they will keep moving to the right. We just looked at this with respect to shifting things right. It can be shift left, it can be circular shift, they can be different variations on this, which we'll look at next. But that's essentially what we are trying to do. We are shifting the contents of the registers. And this is how we do it. We do it using multiple D flip-flops. So let us say that we have a bunch of flip-flops over here, and they are connected in a cascaded manner. As you can see, the output of this flip-flop is connected to the input of the next flip-flop, and so on. And then finally it comes out to the last D flip-flop. All of these are connected to one clock input. They're all synced up with one timing signal called clock. They're all positive edge triggered D flip-flops. So for example, let us say we have an input stream, right? Let us say we have 1, 2, 3, 4. Let's just say we have 5 bit positions, and I'm going to arbitrarily say that this is 1, 0, 0, 1, 1. Let's just say, and we are moving things this way. So tell me what is going to happen here after the first positive edge of the clock. After the first positive edge of the clock, what is going to happen at the Q output of the top D flip-flop? Anyone? Well, this should go to 1, right? Because I am pushing data. The first bit comes in, then the next bit, then the next bit, because the serial input, right? So I'm pushing things this way. First 1 goes in. So as 1 goes in, let me do this. As 1 goes in, the output of the top flip-flop is going to be 1 here. And all the others, I don't know. They are random right now. Because maybe I cleared everything to 0, so they might be all zeros at the beginning. But I only know for sure that after the first positive edge, over there I have a 1. After the next positive edge, what happens? That 1 comes over here, and at the same time the 0 moves in here. So let me write down things this way. Let me write down the first here, then you have it here, right? And then we were there. So after the second positive edge, we are at that place. After the third positive edge, that 1 is going to travel 1 more down. You are going to get the next bit here, 0. That second 0 is going to move down here. Eventually, you will, after you clock everything through, you are going to have what? You are going to have the serial output come out as 1, 0, 0, 1, 1. But it will have to clock through many times because there are 5 bits. It will take in only one bit per positive edge of the clock. So this is very useful for serial communication based on RS-232 protocol. Over here we are going in serially and we are coming out serially. So this is serial in, serial out. Also called as serial in, serial out is also called as serial load and serial access, right? We are reading things serially here, we are writing things serially there. So serial load and serial access, as opposed to parallel load, parallel access, or it could be the combination of serial parallel, any which way. But this is an example of shift registers where you are taking in a serial input bit stream and you are transmitting it through a serial output with a bunch of D flip-flops that are cascaded in the middle. Next, let's do a serial to parallel conversion. All that is different is now we are monitoring the outputs of each flip-flop. So before we were just cascading it, which is still present, we are still cascading it, but now we are also monitoring each output of the flip-flop. So they are still cascaded, right? They are still connected in a sequence, one after the other. So the D input of the next level is connected to the Q, the output of the previous flip-flop. So as you clock things through, they are all positive edge triggered. As you clock things through, your serial output, 1, 0, serial input here, let's say you have the same sequence. After the first positive edge of the clock, this guy will be 1, this guy will be nothing else. After the second positive edge of the clock, 1Q will now be 0. 2Q will be 1. I don't know about anything else. After the third positive edge, 1Q will be 0. 2Q will be 0. 3Q will be 1. I don't know about anything else. But eventually, you will have all those 5 bits available as a serial out over here, but also available in a parallel manner over here. So you can load, so this is a serial load parallel access, or it's a serial access as well, right? Because you always have the ability to read on the last output. So it's serial load. You can access things parallel out or serial out. Both apply over here. All we changed was we observed the outputs of each flip-flop now, giving us the ability to access things parallelly. Earlier, we were just looking at only one serial output, which was the output of the last D flip-flop. And I hope in all of this, you see that the D flip-flops, because they don't have the ability to change the bits, right? They don't have toggle, they don't have set, reset. All you do is you keep the input Q plus equals D, right? So whatever you give at the input, it will be available at the output after the edge of the clock, active edge of the clock. And that aspect of the D flip-flop is what makes it useful in the context of registers. Let's do both, which means now we are trying to do serial access, serial in, parallel out, serial, all the combinations, right? So let's try to see how does that work. The D flip-flops that we have are all positive edge triggered. If I observe the outputs 1Q, 2Q, so on up to NQ, that will be my parallel output. I'm using a load/shift input. let us see, I'm using my load / shift input, which is essentially the most crucial input here, right? So let's see what happens when I make this load or shift input, say act 1. Let's see what happens if it is 1 in red. If that is 1, this is 0, which means these are 0 here. That means that is out, that is out, that is out, right? Essentially means those AND gates will give out a 0. But this guy is in, and in, which means I will have 1D appear over here, 2D appear over here, ND appear over here. The new data inputs that can be serially loaded, 1D, 2D, 3D, and so on, ND. This or this, what will I get? I will get 1D here, 2D there, ND over there. Maybe I put them all at the bottom here. Let's see. Next, I wait for the positive edge of the clock. As soon as I get the positive edge of the clock, 1Q will become 1D. 2Q will become 2D. NQ will become ND. That is how I do parallel in or load, right? So I did a parallel load here. Can I do a parallel access or parallel load, parallel out? Yes, I just observe the outputs of all the flip-flops, and that is me reading things parallelly, all bits at once. So that's fine. Next, let us see what happens when I make this 0. If I make that guy 0, this will be 1. If that is 1, these guys are now going to be active. This is going to be, well, this is not even connected, right? That is 0. That means this is out. This is out. This is out. This is in. Okay. Now, if that is the case, I would have to understand, for the blue, I would have to understand what is coming over here. Well, this is the serial input, right? So serial input here. That means serial input here. So 1Q in this case will be serial input. What about the next one? Well, 1Q is available over there. So this will be 1Q. That means this will be 1Q. That means this will be 1Q. What did I just do? I did a shift, right? That 1Q from the top flip-flop went to the bottom, right? So I just did a shift exactly the way I was doing earlier. What happens to 2Q? It will move down here, right? What happens to NQ? Well, NQ will now be N minus 1 Q. We are writing things down. Okay, N minus 1 Q. So if you really look at just one section here, let's say we observe this. What is that? We again see that this is a 2-to-1 mux. With our control signal being load/shift. when load/shift is 0, what are we doing when it is 0? It's the one in the blue, right? When it is 0, your output is the serial in, right? And over here you have the D input. And when the load/shift signal is 1, the one that we did in red, what do you have there? That means that's when you are doing the parallel input. So we can do the we can do serial and parallel load both over here. All right, questions so far? So I've used serial in, serial and parallel, and also the use of load and access. Load is in, access is out. How to put things into the register and how to read things out of the register, right? Access things. That is output, parallel out. So can I do a serial out here? Yeah, serial out is pretty simple. That is observe NQ. That is your serial out. Where is the parallel out? Parallel out is 1Q, 2Q, 3Q, so on up to NQ. Those are all parallel, all outputs of the D flip-flops being observed at one time. That's your parallel out. So can do serial in, can do parallel in. Where are we doing parallel in? Right here. And also we can do serial out and parallel out. So this slide essentially summarizes all those four options: serial input, serial out, parallel out. So serial input is the shift register doesn't wrap around from right to left. Instead, the user provides the new leftmost bit. So keep inputting the new bit in the topmost D input. And as you clock things through, that bit will keep moving down. It will keep moving right to left. Parallel input is you provide all the inputs of that register at once as a whole word. And then you clock through, that those bits will get inputted, loaded into the register. Serial out, you have to wait for everything to clock through. The last output of the last flip-flop, the output of the last flip-flop is your serial output pin. So you have to wait for everything to get clocked through all the flip-flops to be able to read serially. Of course, we are doing bit by bit communication, so it will take you much longer. However, the advantage of serial communication is the real estate is much smaller, right? So you can you sacrifice time for real estate in that case. Parallel out, well, takes you more space but happens parallelly, so that means time wise it is much faster. But what is parallel out? We are essentially reading or accessing all the outputs of the D flip-flops at once to look at the contents of the register in parallel all at once. The next thing that we talk about is the 74X194, which is a 4-bit bidirectional universal shift register. And the reason why this is a universal shift register, because it can do many things. It can hold data, which means store it, don't let it change. It can shift data right, it can shift data left, it can do a parallel load. So those four are the four modes of the 74X194, which is a bidirectional, it can go either way, universal shift register. Those four modes are set by these two things, S1 and S0. Those are inputs S1 and S0. Now, let us start with the symbol. You have those two setting the mode of the register. There is a SL and SR inputs. You remember at the beginning of this lecture, I said if you are moving things left or if you are moving things right, there will be a need to bring in one more bit. If you are doing circular shift, then fine. But when you are doing a left shift or a right shift, you might need to bring in a new bit. And you can use these two inputs to provide arbitrarily that new bit. Left shift input, right shift input. A, B, C, D, those are your 4 D flip-flop inputs. You can use that for parallel load operation. It's a positive edge triggered design. It has a active low asynchronous clear. Asynchronous meaning outputs can go to any 0. Outputs can all be cleared to 0 at any time. They don't have to wait for the positive edge of the clock. Color code it. Asynchronous clear right there. Then we had positive edge of the clock right there. Parallel load, I need to use all of these, right? I need to use those 4 inputs to do a parallel load. Then I have shift left, shift right if I want to move things left or right over here. Hold data essentially means don't change it. Let it be there. Let it be what it was earlier. So if your S1 and S0 are 0, 0, it holds the data, meaning outputs will not change no matter what you do with it. S1 is 0, S0 is 1, you're doing a shift right. S1 is 1, S0 is 0, you're doing a shift left. And both of them are 1, you're doing a parallel load. So A, B, C, D get loaded into QD, QC, QB, QA. That's essentially changing 4 bits of the register at once. All right. So given all of this, let us take a look at the internals of the universal shift register. So even though this diagram might look very overwhelming, in reality, it is a bunch of 4:1 muxes. So it is repetitive. It is a combination of muxes and D flip-flops. That's it. And the 4:1 mux essentially chooses between one of those 4 options: shift left, shift right, hold, and load. So let us try to take a look at the 4:1 mux here. Let me sketch out for one of them. Let us do it for C. So I'm trying to sketch red box. All right. So my claim is that the red box is a 4:1 mux. And I'm going to take that over here and try to sketch it out in detail. Output, I need 4 inputs here, obviously. One is here, one is here, and then I have a 4:1 mux, so I need 2 inputs for select. Most significant select followed by least significant select. So let me say the inputs. What is the selection based on? The selection is based on S1 and S0. And if you focus on how the things are connected. S1 complement is connected here and here. You see 0 there, 0 there. S0 complement is connected. S0 complement is connected here is 0 and here that's 0. So the selects are S1 and S0 in that order. So let me write those selects here, S1 here and S0 there. So when they are both 0, 0, 1, 1, 0, 1, 1, what happens? So when they are both 0, what happens? You see, if this is 0 and 0, the diagram suggests that this guy will be active, which means all the others will be out. They don't play a role. Now, what is that particular AND gate getting apart from S1 complement and S0 complement? There is a third input there. What is that third input? You see, the third input here is, let me highlight that in blue. That. Which means the current contents of the register are being fed back into it. So even if you clock things through, you will hold the data. That it will not change because you have connected it back in, right? So the current state for C, it's QC, is being fed back over here. So that bit or the D input here will continue to be the previous state. It will not change. So 0, 0, hold data, right? So let me write that over here. What is that? That is current state. Next, 0, 1. So when it is 0, 1, I'm essentially picking this out. Everything else is out. What is that? That is, apart from getting S1 complement and S0, it is also getting a third input. What is that? It is this guy, QB. So QB will come in and get into QC, effectively moving QB up to QC. And moving up is essentially right shift. So I should write over here, right. What's next? 1, 0. For 1, 0, I'm going to erase this here and I'm going to erase this here. For 1, 0, I can also erase this. 1, 0. Topmost is good. All the others are out, which means apart from S1 and S0 complement, what else is the input for the top AND gate? Let's see. This guy is coming from this guy, which is coming from this guy, which is coming from QD. So what happened here? QD moved down to QC. And as you can see, moving down here indicates left shift. Erase, 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 erase. Bring it over here, black, left. So we got current data, that means hold data, don't change it. Right shift, left shift. Let's, obviously the last one should be parallel load. Let us see. 1, 1, right? So for 1, 1, what do you have? Apart from S1 and S0, you have C, the new data coming in. So the new data comes in, gets loaded parallelly, all 4 D flip-flops get it loaded, and QC will change to the new C. So QC plus will be C, right? So that's your parallel load, or the next data, right? Or let me call that new data. And that's your D input. So each one of these red boxes is a 4:1 mux, and the selects are based on S1 and S0. There is a clock input, use an inverter, and feed it into negative edge triggered D flip-flops, making the entire design positive edge triggered. There's an active low clear buffer for fan out purposes connected to the active low clear on each of the 4 D flip-flops. So you can use this to asynchronously clear all the D flip-flops. So you can make QD, QC, QB, QA all go to 0 at once the moment you connect clear_L to low. When you move things left or right, there will be an empty spot. Either it will be on the most significant bit position, or it might be on the least significant bit position. So for example, if you have 1 0 1 1 and you move things left, what happens? Well, if you move things left, this one falls off, right? This one falls off. This becomes 0, that becomes 1, that becomes 1, and there is a new spot, right? There's a new spot open. And because you're shifting things left, you can use LIN, this particular input, to provide arbitrary bit for that new empty spot. And similarly, when you move things right, let's suppose you have 1 0 1 1 and you're moving things right, what happens? Well, this one will move here, that 0 will move here, that one will move here, this one falls off, but there's a new location empty here. Right in can take that arbitrary bit, whatever you provide over there, can take up that position. So those are your left input and right input. A, B, C, D are essentially used to provide the 4-bit in parallel, right? That's for the parallel load. We saw new data coming in. That's what it is used for. I believe that is an exhaustive discussion on the 74X194. Let's see. The question is, if R in or L in is not connected, does it default to 0? No, it doesn't. No, it doesn't. So it doesn't default to 0. If I don't connect left input and right input to anything, then it is going to take up a random value. It doesn't default to 0. All right. Let's move on. We talked about how we can use this shift register to do all of these whole data, shift left, shift right, the use of SL and SR to bring in the new left shift input and right shift input. All right, let's move on. We don't need to discuss this because we have already looked at the 4:1 mux. This is essentially showing it to you again. We already discussed that in a pretty good detail. But if I were to quickly make a 4:1 mux here for this, I would do this, right? One, two, three, 4. I would say S1, S0 as always. 0, 0, 0, 1, 1, 0, 1, 1. And that bit essentially is connected here, right? The input to that is, when it is 0, 0, it is QC. and when it is 0, 1, QB, when it is 1, 0, QD, and when it is 1, 1, C. So hold left shift right, hold, then we did right shift, then we did left shift, then we did new data. All right. Application modem, universal asynchronous receiver transmitter. Just a few, literature survey here. A transmit on the UART reads a word in parallel from a computer, then writes it bit by bit to a serial data communications line. So this is a parallel, reads word in parallel. So parallel access from a computer, then load it bit by bit. So serial in, right? Parallel out, serial in. For a receiver of that modem, you read word by word bit by bit on a serial line. Then the computer reads the word back in parallel format. So eventually, if things are parallel versus parallel, in the middle, the communication is happening on a serial line, right? So you convert from parallel to serial, you do the communication on serial, and then you change from serial to parallel. Now here is, there are two more examples that are pretty interesting that are left over. One is the ring counter, and then there is a Johnson counter. Before we do anything, I want to ask you, when you think of a counter, say a 4-bit counter, not even a 4-bit counter, let's say a 3-bit counter. What would you want this 3-bit counter to, some of the qualities of this 3-bit counter? So think about any counter, right? So think about 0, 0, 0. Say, let's do this. Let's make this into a Q2, Q1, Q0. When you think about a 3-bit counter, I picture this. 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Right, which means I'm going from 0, 1, 2, so on up to 7, right? But this is, probably the most basic counter. Why? Because it has all the 8 states in it. There is no skipping of states. It doesn't go from 0, 4, 5, 7 back to 0. It doesn't skip any states. It goes over each and every value. And it is counting in a pattern, right? It always increments by 1. So it's a 3-bit up counter. But counters can come in various different forms. They can do, for example, they can just go 0, 1, 4, 7, back to 0, 1, 4, 7, and so on. So the counting sequence doesn't have to follow this sort of a traditional way of counting. Counters can come in different forms. However, if you're designing a counter from scratch, you would want it to have as many of those 8 possibilities as possible, right? If the counter is 3-bit, then there are a total of 8 possibilities for the output, and you would want all those 8 possibilities in that counter output. Also, you might want to design a counter in such a way that you don't get stuck into a loop. For example, what if you have 0, 1, 2, and back to 0? You wanted to design it in such a way that, you don't want it to get into a loop, meaning if it goes from 0, 1, 2 back to 0, and then it never comes out of that 0, it doesn't count at all, right? So you don't want that counter to get stuck like that. So those are some aspects of counter that you might want to consider while designing, say, a 3-bit counter. What we have next is a ring counter. And there is a reason why it's called a ring counter, because there's a circular shifting nature to this. And this ring counter is based on 74x194, the bidirectional universal shift register. And the claim is that we have wired it as a shift left shift register. That means out of the 4 modes, we have made sure that we pick the shift left mode. What is that mode? S1 is 1 and S0 is 0, right? So this is S1 is 1 and S0 is 0. We have already taken care of 1. We have hardwired S1 to +5. So that's taken care of already. S0, well, we have connected it to a signal called reset or load. So we are essentially using this to do a parallel load initially, and then we make it 0 so that it does a left shift operation. So at the beginning, so let's see, equals 1 to do parallel load at the beginning. And then make it 0. So only for a short duration of time at the beginning of the counting, we have connected it to 1 so that we can do a parallel load, which means A, B, C, D get parallelly loaded into QD, QC, QB, QA, all the 4 D flip-flops at once. It's a positive edge triggered design. So clock input on the positive edge of the clock, that's fine. We have an active low clear. We have an active low clear input, which we have connected it to +5, which means we are never clearing. Never clear, right? Clear will always be inactive. We have hardwired D to +5, as you can see. So D is equal to 1, hardwired. C, B, and A are hardwired to 0. Left input is hardwired to QA. Left input is hardwired to QA. Now, what is going to happen at the beginning? Well, we already claimed that at the beginning, we are going to make S0, this signal 1. When you make this 1 and you have a positive edge of the clock, what is going to happen? We do a parallel load at the beginning, which means these guys, Q0, Q1, Q2, Q3, will be the same. Soon after the positive edge of the clock, they will be 1, 0, 0, 0. After the positive edge of the clock, soon after that. Once we have an initial count, what we are going to do is we are going to change the S0 to 0. We are going to make this 0 now. Once we make it 0, it will be in the left shift register mode. Left shift register mode meaning QD will move to QC, QC will move down to QB, QB will move down to QA, QA will move back into the left input, which will again come back to QD. So let's see what's going to happen. After we make that change for the mode, we have now set S0 to 0. After the next positive edge of the clock, what is going to happen? What is Q0 going to be after the next positive edge of the clock? Anyone? We have set it now as a left shift register. you know the current values of Q0, Q1, Q2, Q3. After the next positive edge of the clock, what is going to be Q0? We just have to see what happens to Q0. Q0 is coming from what? Q0 in this case is now going to come from the left input, right? Because things are moving down. So when you move things down, QD goes to QC, but what happens to QD? Well, QD has to bring in the new input, left input, L in. L in is connected back to QA, which is 0 in this case. So 0 comes in on Q0. This guy 1 will move down here, this 0 will move down here, this 0 will move down here. You guys see that? After the next positive edge, again, your left input is still 0. So a new that same 0 based on this wire will come back in. That 0 will move here, this one will move here, that 0 will move there. What happens next? After the next positive edge of the clock, still QA is 0. So again another 0. This 0 will move down, this 0 will move down, this one will move down. What happens to Q0 after the next positive edge of the clock? After the next positive edge of the clock, Q0 will now be 1 because QA has changed. The new left input is 1. And then this 0 will come down, this 0 will come down, this 0 will come down. Notice where we are. We started with 1 0 0 0. We came back to it after 1, 2, 3, 4 clock cycles. And this is going to be a counter because this is going to keep going in this pattern because this is a static structure now. In terms of decimal, what does this look like? Q3, Q2, Q1, Q0, 0, 0, 0, 1. So that's 1. 0, 0, 1, 0. That's 2. Decimal 2. 0, 1, 0, 0. That's decimal 4. 1, 0, 0, 0. Decimal 8. Back to 0, 0, 0, 1. So this particular ring counter has 4 states. It counts 1, 2, 4, 8. Back to 1, 2, 4, 8. 1, 2, 4, 8. 1, 2, 4, 8. And it keeps going. So out of the 16 possible states that a 4-bit counter can have, this particular ring counter is only useful for 4 states. So it's not particularly exciting. But a really big problem with this ring counter is this. If any one of these ones gets corrupted and it accidentally becomes a 0, what is going to happen? If it accidentally becomes a 0, your counter will forever be stuck at 0. It will never go anywhere. It will be stuck at 0. So if you have an error in the 1, you have a major problem then. It will never come out of that 0 state. All of this is explained with a timing diagram for the ring counter over here. Clock is going up and down. So all the positive edges of the clock have been highlighted. The reset signal, which was also initially used for loading, parallel loading, is shown over here. So initially it is in the load mode, and then after that it is in the shift left mode. So when it is 1 and there is a positive edge of the clock, we load Q0, Q1, Q2, Q3, which will be what? This is 1 there, 0 there, 0 there, and 0 there, just as we saw over here. 1, 0, 0, 0. Then after the next positive edge, after we loaded, we made it into a shift left, right? So at this point, we transitioned from a parallel load mode into a left shift register mode by adjusting S0. And as you are clocking things through, what happens? That one is now coming down. So this guy will go up here, 0, 1, 0, 0, followed by 0, 0, 1, 0, then 0, 0, 1, 0, 1, and then that one will come back here. And this cycle will continue. And that we called it decimal 1, decimal 2, decimal 4, decimal 8, back to decimal 1. So only 4 states. What are those 4 states? S1, S2, S3, S4, and we are back to S1. So 4 out of the ideal 16 possibilities for a 4-bit counter. So this is a 4-bit counter that only has 4 states. So a little bit useful. It is simple, but not too useful. But it has a very, very big problem that if any one of these ones gets corrupted to a 0, the ring counter will be stuck at 0. It will never move to any other count. The last counter on this lecture is the Johnson counter. So all we did was we added this. It is very similar to the ring counter with some adjustments. Over here we have hardwired S0 to 0. So we have made sure that it is always going to be in the shift left register mode as far as S0 is concerned. But S1 is also connected to +5. So always going to be in the left shift register mode. Clock is connected to the positive edge of the clock, so we can clock things through. Reset underscore is you have an active low clear input. We can perhaps use this reset to initialize the design. Start off with 0, 0, 0, 0, right? So let us do some counts here. So what is going to happen? Let us suppose we do this for the reset. For the reset, we start off low and then we make it high. When it is low, we clear it, right? Because it's active low input. What is going to happen? This will be all zeros now. And because Q3 is 0, you have a 1 there. That means you have a 1 over here. So what is going to happen at the next positive edge of the clock? The next positive edge of the clock, this guy will become a 1, and then it's going to shift down. So 0 here, 0 here, 0 here. After the next positive edge, 1, 1, 0, 0. Because again, that 0, the last 0 will be fed back. The inverted version will be fed back. And then you have 1, 1, 1, 0. So you will first have a bunch of 1s fill in, and then you will have a bunch of zeros that will start filling in. So in this case, you will have S1 all the way to S8, 8 different states. For the first 4, that 1 will come in, more and more ones will come in, and then in the last 4, more and more zeros will come into the counts. So let me write those out. So initially you start off at 4 zeros, so you have the state 0. Then after the first positive edge of the clock, it will go to 1 here, zeros. So that's decimal 1. After that, you have 1, 1, 0, 0. So that is decimal what? 3. After that, you have 1, 1, 1, 1, 0. That is decimal 7. After that, 1, 1, 1, 1. Decimal 15. That's when your last 1, 1, 1, 1 is. Now, because the complement of Q3 is fed back, now zeros will start coming in. So now 0, 1, 1, 1. What is that? Decimal 1, 1, 1, 0, right? Where is blue? Blue is right here. This is 12 plus 2, 14. Next, 1, 1, 0, 0. That's 12. Next, 1, 0, 0, 0. That's 8. And then we'll, once we cycle one more through, you have 0, 0, 0, 0, 0, 0. That's 0. We are back to where we started. So in this case, there are 8 states, so a little bit better than ring counter. But another advantage over here is because there is a NOT gate involved, even if some bits get corrupted, there is a way to come back to the normal counting sequence because of that. So it's not as bad as ring counter as far as corruption of a bit is concerned. So it does better in terms of the number of states it's able to express in its outputs, and it's also doing better in terms of how it handles those errors, bit errors. Okay, well, that's all I had in mind with respect to the registers discussion. Let me stop the recording here.